Aim of the experiment to verify Norton's theorem. Apparatus required a variable regulated power supply, 3 resistors, a resistance box, a constant current source, a the milliammeter and connecting wires. Theory according to the Norton's theorem. Any linear two-terminal network containing resistances, voltage and or current sources can be replaced by a single current source in parallel with single resistance Rn. The Norton's equivalent wherein is the short circuit current between the two terminals and Rn is the resistance between the terminals when all the voltage sources in the network are short circuited and circuited. All the current sources are open. Key Fig B shows the Norton's equivalent circuit of the network. Fig A herein is the short circuit current between the terminals. And B when RL is removed of the circuit. Fig A shows the above condition. Thus, the value of short circuit current in equals VR plus R2 R3 R_2 plus R_3. VR2 RL R2 plus R3 plus R2 R3 L_2. R_2 plus R_3. In equals thus, the value of resistance Rn R_n equals Rtn equals R_1 asterisk R_2 R_1 plus R_2 plus R_3 formula used, in equals VR2 R_1. R_2 plus R_3 plus R2 R3 R_n equals R_1 asterisk R_2 R_1 plus R_2 plus R_3.
Figure. Procedure. First point, keep all the resistance close to their maximum respective values. Second point, close the switch S1 to R and S to CC positions. Observe the load current I and voltage VL readings. Then, the load resistance is RL equals VL. I. Third point, short the load terminals and find the short circuit current in. Fourth point, next compute the resistance Rn of the network is seen from the load terminals. Replace the 220 V Saveche by a shout by closing S1 to B. Apply V equals HOV at the output terminals. Closing S2 to DD. Read the current from ammeter. We get Rn equals V. I. Fifth point, now compute the load variant 2 by applying Norton's theorem. E equals in asterisk Rn plus R. Sixth point, compare the above computed load current with its observed value in step 2 and verify the theorem.
Observation table. Calculations. For first reading, V equals 110 volts, R1 equals 100 ohm, R2 equals 90 ohm, R3 equals 15 ohm, V equals 85.1610 VRL equals VL divide IL. RL equals 85.161 volts divide 0.28387, RL equals 300 ohm, Rn equals V divide Rn equals 110 divide 0.50769, Rn equals 216.67 ohm, EL equals in multiply Rn plus RL. IL equals 0.67692 multiply 216.67 216.67 plus 30 DI, L equals 146 multiply 668256 516 asterisk 67, EL equals 0.28387 AV equals 81053 V. For second reading, V equals 150 volts, R1 equals 150 ohm, R2 equals 250 ohm, R3 equals 200 ohm, RL equals VL divide IL. RL equals 81.053 divide 0.23158, RL equals 350 ohm, Rn equals V divide Rn equals 150 divide 0.61538, Rn equals 243.75 ohm, EL equals in multiply Rn divide Rn plus RL, EL equals 0.56410 multiply 243.75 divide 243.75 plus 350 IL equals 137.49 divide 593. 75 EL equals 0.23158 A.
Result, the measured values of the load variant 2 and the load voltage VL for each value of RL in the original circuit match with the corresponding values in the Norton's equivalent circuit. For first case readings, Rn calculated equals 216.67 ohm, Rn measured equals 216.67 ohm, in calculated equals 0.67692 A, in measured equals 0.67692 A, il calculated equals 0.28387 A, measured equals 0.28387 A. For second case readings, Rn calculated equals 243.75 ohm, Rn measured equals 243.75 ohm, in calculated, equals 0.56410 A in, measured, equals 0.56410 A il, calculated, equals 0.23158 A il, measured, equals 0.23158 A. In both the two cases, calculated and measured values are same. Hence, Norton's theorem verified. Precautions and sources of error. First point, the current in the circuit should remain constant for all the observations. Second point, the internal resistance of the power supply, if any, is neglected. Third point, the values of the resistances used in the circuit should be checked with an ohm meter. Fourth point, the power supply should be switched off while making or breaking the circuit.